Good morning, good afternoon, good evening, and welcome to Day 3 of the 2021 NASA Earth Science Applications Week. This week, we are celebrating the many ways NASA Earth Science helps make our world a better place and celebrate the official 20th anniversary of the NASA Applied Sciences program. Thank you so much for all who are joining us from across the globe. My name is Brittany Beaudry, and I'm a fellow with the NASA-developed national program at Ames Research Center, and I will be your MC for our first session today, which is Enhancing Water Management. As a reminder, you can find the complete agenda and links to all events on the NASA Earth Science Applications Week event webpage. Should any changes occur, the most up-to-date schedule will be found there. For a brief summary, we will kick off each day with plenary sessions from 12 p.m. to 2 p.m. Eastern Time on Zoom, the same link that you used to join us today. Following the daily plenary sessions, we will have a networking social on Thursday on a platform called Wonder and 2 concurrent tracks of events in the afternoon symposium later today via Microsoft Teams. All events this week can be joined directly from your browser, and all links are available on the event webpage, which I highly recommend you visit. Given the number of attendees, speakers, and events we have occurring this week, we would like to thank you in advance for your patience with any technical difficulties that we may encounter. A few housekeeping items before we begin today's plenary session. Know that everyone is automatically muted, so we hope you'll use the chat function for any comments you may have and direct questions to our speakers in the Q&A section. And now, without further ado, it is my pleasure to introduce Dr. Nancy Searby, Program Manager of NASA's Capacity Building Program, who will share some opening remarks.
Great, thank you so much. My camera says I'm blocked from showing it, so I will speak. Again, as you introduced me, my name is Nancy Searby, and I manage our capacity building program. And you say, what does that mean? And so our capacity building program really is all about building the skills to use our Earth observations. It's really important that if you know a lot already, maybe you need to just know the latest and greatest, attend an RSET training. If you want a little more deeper experience, maybe you want to join Develop and do a 10-week project with Develop and other partners to apply Earth sciences. Or maybe you want to actually engage in a more deeper project that actually is co-development with users in Africa, Asia, and the Americas. So maybe you want to apply to the Open Severe Applied Sciences team solicitation. We have lots of different ways that we think about building the skills of others to use our Earth observation information. I wanted to just invite you to participate fully today. I know this is the third day now, and so everybody might be feeling a bit stretched, but this is a great day to participate. And so we are talking about first water. And so my question, as everybody's chatting and introducing yourself, I'm going to ask you trivia questions, and you can put your answers in the chat as well. So water is a basic element of life, right? So enhancing water management is really important. So how long can we as humans survive without water? Put it in the chat. The second thing we'll be talking about is food security. We also need food. How many days can we go without food? Other thing to put in the chat. And if you're really interested in food and drink, the exciting thing is that NASA has a communications campaign. That's what we call something where we focus on a particular set of topics going on right now. So if you go to the nasa.gov website, you'll see something called Food and Drink, where we're talking about all the ways that NASA engages with things you eat and things you drink. So please do come to those plenary sessions to learn more about what we're doing. Another thing I think you'll see is that we really talk about our partnerships with others and how important it is. NASA cannot do it alone. We really do need partners. So you'll hear that from our agricultural program called Harvest. You'll hear that from our Western Water Applications Office, and you'll hear that from Develop, where we even have a partner participating. After you've been sated by your food and drink sessions in the plenary, please do come back for the afternoon symposium. There are 2 tracks. Please hop back and forth. Think of it like a science conference where you pop over and see a talk and then you go see another one, so that we can fully participate in all of those. The Severe program is going to be talking about the way we do our work, which is through service planning And it's a really important update that has just been made to our toolkit to really fully consider gender and how that affects how we do our work. Also, we really do care about the impact of our Earth observations, and Valuables has been this great effort really trying to help us move the field forward to be able to assess the impact of our work economically. There's also great flash talks. You can see a story map to learn more about the capacity building program. And you'll see lots of examples of how important it is to work alongside partners, to co-develop the applications, how important it is to be inclusive and to think equitably and act equitably, and the importance actually of social science as well as the more traditional harder earth sciences to doing our work. So with that, I'll hand it back, and I hope you participate and enjoy the day. Thanks.
Thank you so much, Nancy, for your thoughtful words. I would now like to begin our first session today, which is enhancing water management. So to start, John Bolton will tell us about leveraging data and tools to develop new capabilities.
Thank you, Brittany. And another fun fact about water, water is the only substance on Earth that's naturally occurring as a solid, liquid, and gas. So that's another fun fact for water. So my name is John Bolton. I'm a research scientist at the Goddard Space Flight Center. I also serve as the Associate Program Manager for Water Resources. And I've been involved in many different aspects of the applied sciences program. So I'm honored to be here and help kick this off. Next slide, please. So first, we're going to go back to our middle school science. This cartoon shows Earth as a complex, interrelated system. I like to say it's actually a system of systems. If you look at this cartoon, everything that we see here that is blue, white, or green really involves water or the movement of water. Now, I'd like to bring your attention to the yellow text here. These are the fluxes between the atmosphere and the ocean, the land surface and the atmosphere, and the ocean and the land. So our job as scientists and engineers is to monitor and as accurately as possible predict and monitor and constrain each component of this complex interrelated system so that we can have a holistic view of how the world works. So it's really, we have an opportunity to do this at NASA Applied Sciences, and really probably a responsibility for doing this since we're able to better manage our world in a better way. Next slide, please. So in fact, that's what the NASA Water Resources Program does. Each one of these blocks is actually one of the storages from the previous cartoon. And we have over 30 active projects that are focused on assessing different aspects of water availability, water use, water quality, essentially the management and preservation of this precious resource. So what NASA's Applied Sciences Program does is really bridging the gap between NASA Earth observations and society. How do we better inform society? How do we make better decisions for managing water across the board and through this system of systems? So we have many different ways that we're doing this, whether it's assessing fire risk, whether we're looking at the mega drought that's happening in the Western United States right now, or perhaps looking at the Grand Ethiopian Renaissance Dam and assessing how those impacts from that filling may be affecting the local groups in that region. Next slide, please. So what we see here, this is Allison Felix, and she is being passed the baton during the Tokyo 2021 Olympics. And I'm calling this, she's passing this baton from concepts to capabilities. But the question is, what is the baton? The baton could be an idea. The baton could be research, even mentorship or applications or capabilities. So in fact, within the NASA Applied Sciences program, what we're really doing, we're running this race and we're passing this baton and we're building a team of runners essentially for helping move from concepts to capabilities. And just fun fact, so Allison is now she has been the most decorated female athlete in the history of the Olympics from this. Next slide, please. So earlier this summer, Dr. Karen St. Germain visited NASA Goddard Space Flight Center, And she addressed the Global Risks Report from 2021 that was published by the World Economic Forum. And she stated that we are in a pivotal point in our humanity. And because we are at risk of climate action failure. And because of this, she highlighted the need for an urgent water security and food system resilience. And how is this done? This is done by the need to translate data to actionable information. So moving from data to decision making. And this is really the mission statement of the Applied Sciences program. And it's woven very, very closely to many aspects of water resource management, not only within the science and projects that we're seeing today, but also through the different programs within the NASA Applied Sciences program. Next slide, please. So one part of running a race is that you are part of a team. And when you are part of a team, you enable new capabilities. So through this teamwork, and here we're seeing Allison's fancy new innovative shoes that she was wearing. And just fun fact, she is selling these shoes and donating them to charity. So if anyone's interested, contact Allison. But through this, we are cultivating a reinvigoration of data and tools through innovation, through test beds, and through this teamwork. Next slide, please. So one example of true innovation is the Ellicott City flood prediction. This photo, right now I'm sitting about 1 mile from where these photos were taken. On the left was the 1972 flood from Agnes, and on the right was the 2016. So essentially in a matter of minutes, the downtown Ellicott City moves from a beautiful street to a severe flash flood. They've had over 1,000-year flood events in the past 10 years. So what we've been doing through the NASA Applied Sciences program, we were partnering with the Howard County Office of Emergency Management. And what's really cool is this project started through the NASA Develop project. And we've been partnering with SSSAI and our friends at the National Weather Service. But it's given us an opportunity of taking a bit of a higher risk approach and looking at machine learning and deep learning capability. So just even 10 years ago, this idea of artificial intelligence was conceived as considered a bit of a black box concept, but now we're embracing this technology and moving forward and working with partners, and we're able to test and demonstrate the utility of these innovative sciences and techniques and move towards truly innovative and novel decision-making capabilities. So essentially on the right, what the little cartoon, I think the little movie ended, but we've moved from this concept of what would happen if we're enabling an early warning for a flood to actually taking this operational concept and providing an operational flood warning dashboard for our friends at the Howard County Office of Emergency Management. And I just have to say, this project is very dear to me and my friends in my community, and it's quite an honor to be able to contribute to our society in my backyard and our neighborhood. Next slide, please. So as I mentioned, there is teamwork involved when you're running this race. And there are new teams. When you go around the lap one time, the race isn't over. You pass that baton. So through innovation, there's a cross-pollination of ideas and capabilities from scientists and partnerships, and also between the NASA programs. And that's what I'd like to emphasize with the remaining portion of my presentation. Next slide, please. So when you're in a race, you can't stop. You got to keep moving. And that's what's really cool about this right here. Essentially, this is the soil water assessment tool. It's one of the most widely used hydrologic models in the world. And we've coupled this with NASA Earth observations. And by doing this, it's really improved its utility in regions of the world that are water insecure, that tend to have poorly gauged regions. But essentially, this concept started in 2014 with the Develop program. And then it was able to be supported through the Disasters program, as well as the NASA Severe program. It's being leveraged in the ecological forecasting, as well as the Water Resources program. And now we've transitioned to working with our friends at the Mekong River Commission. And now it's an integral part of the Department of State the ISAD, which is the Interagency Water Working Group Science Applications Team. It's a mouthful. But the point here is this race has kept moving since 2014. And just 2 weeks ago, we had a workshop, a training workshop with over 100 participants in the Mekong region with the very high level members of the Mekong River Commission, as well as our friends at the at K-Water, the Republic of Korea, and USAID. Next slide, please. So science has momentum. A race has momentum, so you have to keep running. What's really cool, this is the cover of Nature was just pushed out on Friday. So the August 5th cover of Nature, it features a previous developer. People may remember Colin Doyle. And Colin Doyle, in fact, was a part of that earlier work through Develop, where we were working with the Mekong River Commission. And Colin is working with Cloud to Street. And what they're doing is they're building a database, a global flood database, and they've just published a paper looking at satellite imaging and looking at the proportion of the global population that is exposed to floods. So I was very, very excited. Colin just sent me an email yesterday. You mentioned it. Next slide, please. So my last example is passing the baton to Argentina. This is another example of science moving forward and partnering with international partners. We just had a handoff yesterday with our NASA Develop team with the Buenos Aires Grant Exchange. And to quote Esteban Capote, he said, "To come up with a tool like this for us is incredible. Essentially, we're taking the widely used normalized difference vegetation index, and we're forecasting that up to 3 months in advance for allowing monitoring and forecasting of future agricultural yield." Next slide. And that's it. In the end of the race, we all win. So thank you very much for your time, and I look forward to our discussions later this afternoon.
John, thank you so much for that interesting presentation. Up next, Christine Lee will tell us about missions and apps for water resources management.
Great, thank you. Can you hear me okay, Brittany?
Yes, I can.
That's good. Okay, great. Thank you everyone for the chance to talk about Earth science mission efforts and the important work that various Earth science missions are doing as they relate to water resources. My name is Christine Lee, and I am a scientist at the Jet Propulsion Laboratory in the Water and Ecosystems Group. I'm involved with a couple of different Earth science missions at various stages, and I'm also one of the associate program managers, like John Bolton, for the Water Resources Program. Next slide, please. Thank you. So we have over 20 Earth science missions in various phases of development and operations within the Earth Science Division. And a large portion of these missions are extremely relevant to water resources, applications, and management. And so I wanted to take some of our time today to talk about a couple of examples that the Water Resources team has been involved with. Next slide, please. And before I jump into those examples, I also wanted to acknowledge, of course, the recent announcement that from NASA to support the NASA Earth System Observatory to help address and mitigate climate change through a collection of 4 to 5 different Earth system platforms, studying different aspects of Earth from the atmospheres to our oceans to the land and so forth. And I will provide a little bit more information on 2 of these. Next slide, please. So the first Earth science mission that I wanted to mention that we've been heavily involved with is the Soil Moisture Active Passive mission. And SMAP, also known as SMAP, is a global mission to map soil moisture and determine freeze-thaw states using active and passive radar. Soil moisture is an extremely important part of understanding our water cycle, but it's also really critical in improving various applications that you see here. Currently, SMAP is delivering soil moisture information at 9-kilometer resolution as a standard product every 2 to 3 days. And some of the ways in which SMAP is supporting societal benefit areas related to water is through improving weather forecasts and stream flow hydrologic models through agricultural monitoring and irrigation, as well as flood and drought forecasting. There are other ways that SMAP is providing societal benefit in areas that are adjacent to water resources that you can see listed here. But more information can be found online, and I'm happy to connect with those of you who may want to learn more about some of these other application areas as well. Next slide, thank you. The next mission that I wanted to call out is SWOT, the Surface Water Ocean Topography Mission. The current launch window is in 2022, also intended to be a global mission with a 21-day revisit, 1 kilometer spatial resolution, with the goal of better understanding changes in our world's oceans, as well as terrestrial surface waters. So SWOT is really cool in that it's going to help us resolve our terrestrial surface waters in terms of river height, reservoir height, and so forth. And it's going to provide us a ton of additional information on the state of our rivers. Some of the common application areas for SWOT, as you can see, are listed here. Most of them span hydrology to ocean applications, but I'll just do a call out to drought and reservoir management. And so being able to have detailed information on reservoir height and state is very important to our reservoir operators, especially as they make decisions on releases to mitigate for flood risk, or whether they need to hold back waters under drought conditions. Next slide, please. So I'm now going to talk about mass change, which is one of the missions that is identified in the decadal survey and is part of the NASA Earth System Observatory that I mentioned previously. It is essentially part of the kind of GRACE and GRACE follow-on series of mass change observations, which have really allowed us to understand the change in terrestrial water storage over the last almost nearly 20 years record that we have. And this has been really important in helping us understand the relationship between potential changes in terrestrial water storage and human activity, being able to link depletion or groundwater pumping with changes in water storage. And so this is a really critical mission that will help support this continued record in our understanding of the water cycle. Some of the different application areas that mass change will touch include improving our understanding of drought and flood, agriculture, and then some of these other areas, including sea level rise and natural hazards. I couldn't find a more recent image of mass change, so I put up GRACE follow-on. It'll likely have a very similar architecture of having 2 nearly identical satellites and being able to assess changes in gravity through changes in mass and movement of water on the Earth's surface and subsurface. Next slide, please. So one of the projects that I'm working on now is EcoStress, the Ecosystem Spaceborne Thermal Radiometer Experiment on Space Station. We're on the International Space Station, launched in 2018, and able to help resolve evapotranspiration at a 1 to 5 day revisit at 70 meter spatial resolution. I know I'm running out of time, so I'll just note that this has been one of the funnest projects to be a part of. It has a ton of different application areas that you can see listed here. Next slide. And then the last one that I'll mention is the Surface Biology and Geology Earth Observing System, also part of the Earth System Observatory suite. It's envisioned as 2 platforms, a visible to shortwave infrared imaging spectrometer at 30 meter resolution, 16-day revisit, and a thermal at a 1 to 3 day revisit. And this is going to have a variety of applications as well, and be really critical, especially in partnership with the other ESOs, to understand impacts of climate change. So I will end there, and then just extend, feel free to contact me if you'd like to learn more. Thanks.
That was really captivating. Thank you, Christine. Next, we have Stephanie Granger to tell us about fostering partnerships through needs assessment.
Good morning, everyone. Good afternoon to those on the East Coast. My name is Stephanie Granger, and I'm the group supervisor for the Applied Science Systems Engineering Group at the Jet Propulsion Laboratory in Pasadena, California. And I'm also the program strategist for the Western Water Applications Office, the NASA Western Water Applications Office. Next slide, please. So I really love this quote from Brian O'Neill about partnerships. And the way it was really found that the door to partnering and mutual understanding often opens with a conversation about a need. An activity of the Western Water Applications Office is to conduct management studies and needs assessments. And I'm not going to read the bullets, but for the first bullet, I'll relate those in terms of capacity building. But we sort of identify the needs and how NASA data can add value. And that's really building capacity both on the practitioner side as well as on the scientist side. Developing projects, we co-develop projects based on these needs with our practitioner partners. And then lastly, we make these needs, we've developed a needs catalog that we make widely available to the applied science community, sort of building capacity to the applied science community to understand critical challenges in the Western US and to help address them. But a real benefit from the needs assessments are the partnerships that have taken root and flourished. Next slide. So kind of to set the stage in the Western US, water management in the Western US is historically complex, both in its legal and organizational frameworks. There's a lot of players. It is often litigious. Powell's quote on the left is just terrific and true to this day. And today, water resources in the Western US are further stressed by growing populations, changes in land use, and impacts on climate change on an already overallocated system. So in order to understand this sweet spot where Earth observations and NASA science and expertise can add value to water management, we conduct needs assessments. So just in a nutshell, the needs assessments that we conduct are via a multi-step iterative process where we work with a local consulting firm to conduct background research and partner interviews. We lead a webinar to communicate the goals and objectives of an in-person assessment. And then we facilitate the in-person assessment where we work with our partners to develop use cases along with the high-level requirements. I'll provide some examples of partnerships through needs assessments conducted in the Colorado and Columbia River Basin. Next slide. So one of our first needs assessments was for the upper and lower Colorado River Basin. It was a diverse set of stakeholders who attended. We identified a number of different needs, including water supply, especially snow and runoff forecasting, consumptive use, and drought monitoring at the state level. Notable partnerships that were established as a result of this needs assessment include two project partner organizations. First, the Colorado State Climatologist Office, working with a team from Goddard Space Flight Center to develop an instance of the land data assimilation for drought monitoring and assessment. That team at Goddard is led by Jessica Erlingus. The second project partner organization was the U.S. Bureau of Reclamation and the Upper Colorado River Conservation District. And this project has been the partnership has been realized through an ET intercomparison project in the Upper Basin led by Chris Hain at Marshall Space Flight Center. Kind of more on the programmatic side, WAO was invited, as a result of this assessment, WAO was invited to participate in the Colorado River Hydrology and Climate Work Group. And this work group is really a boundary organization made up of practitioners and water managers representing across the entire basin, working together to develop solutions, identify gaps, and funding sources to improve modeling and monitoring in the basin. It's just an incredible window into the entire practitioner community in the Colorado River Basin, and we are fortunate to be a part of it. Next slide, please. A recent needs assessment was conducted for the Columbia River Basin. We brought together 27 practitioners and we identified a number of needs in water supply, snow again, no surprise, watershed health, specifically around fisheries, salmon fisheries, water quality, mostly as it relates to impacts of wildfire, and agriculture. Notable partnerships that have been established through this needs assessment are a joint WAO and USDA NRCS collaboration to evaluate the use of snow data in forecast models and for quality control. And then several potential partners with federal and state agencies and NGOs, including the Columbia River Intertribal Fish Commission. One notable outcome here was that a new connection was made among state water managers who met at the in-person assessment. And this resulted in a proposed multi-state effort around open ET. So we think that the WAO, we like to think that the WAO was a catalyst for this interstate cooperation. Next slide, please. This is my last. Just in closing, trust is key. So we found, especially in Western water management, NASA is unique in this domain as we don't have a mandate in water, and we are inherently a trusted broker of information. However, these sustained relationships are sometimes difficult to maintain. So the WAO is uniquely poised to sustain strong relationships and also to develop new partnerships with well-understood goals through its needs assessment process. Thank you so much.
That was great, Stephanie. Thank you for sharing that with us today. Next, we have Venkat Lakshmi here to speak about the use of modeling and remote sensing to study the water cycle.
Hi, can you hear me?
Yes, I can.
Can you see me? Can you see me
Yeah.
too?
Yeah.
Thank you. Thank you so very much, everyone, for setting such a great stage for this morning session. I would like to pick up on where John Bolton left off about the Olympics and try to brag that University of Virginia won 9 medals in the Olympics, 2 golds, 4 silvers, and 3 bronze medals. And the most important gold coming from the women's basketball team, which is coached by Dawn Staley, one of our most famous basketball and UVA alums. And I also want to give a shout out to our team, which is the Tondi Sap agricultural team with Brian, Joey, Justin, Molly, and Nick. Thank you so very much. So I'll start off with this project by saying the statement of the problem is very simple. In most countries of the world, the lack of observations of stream flow or precipitation necessitates use of satellite data and modeling. Most of the places in the world have numerous problems, especially the developing countries of the world have numerous problems with land use and land cover changes, which make impacts on stream flow, especially the nutrients coming in from agriculture, which I will talk in a minute. Use of hydrological modeling is very important also to determine impact of climate change. These days there are very readily available data sets for future precipitation and temperature, which can be used as forcing for offline hydrological models, and you can see what's going to happen with your stream flow, the timing of your stream flow, the volume of your stream flow, etc. The first point leads to water quality. Water quality in lakes, rivers, impacts drinking water and aquatic life. In many countries of the world which lack access to treated water, they take water directly from lakes or rivers, and this means that you want to have ensure some minimal level of quality. And then of course the age-old problem of trying to balance agriculture and power production. Next slide, please. So I'm going to talk very quickly about the stream flow and nutrients in the Ganga River Basin. Next slide, please. So the Ganga River Basin is a very large river basin in India and provides food and sustenance to about 500 million people. And the river itself is about 2,500 kilometers long, and the watershed is over 1 million square kilometers. And about 1/3 of the Indian population depends on this watershed and this river for sustenance. There are about 100 gauging stations run by the Central Water Commission, even though the data is not necessarily always available. And there are 38 nutrient sampling stations. And then we have had a strong relationship with the Dartmouth Flood Observatory. One of their authors, the person who is associated with that, Rob Brackenridge, was on that paper which John Bolton showed. Next slide, please. So in every watershed, when we work with modeling, you have to understand the characteristics of the watershed, the digital elevation model, the land use, land cover, the soils, and the slope. This is what we call sometimes as the static data. DEM, soils, and slope are static. Land use, land cover is dynamic, mostly provided by MODIS, a NASA sensor. Next slide, please. So an example of what we do is we use readily available off-the-shelf hydrological models. This one is the soil water assessment tool model. In the past, we have worked along with John Bolton and his team at NASA Goddard for working on this. And then you can see that the calibration and the validation of this model at parts is pretty good. Next slide, please. What is more interesting to us is verification also with satellite-based data. The Dartmouth Flood Observatory is based on satellite observations and retrieval of discharge. And you can see these are a couple of sites along the stem of the main Ganga River. And you can see that these do a reasonably good job of simulating the discharge as viewed by the Dartmouth Flood Observatory, or as observed by the Dartmouth Flood Observatory. Next slide, please. So one of the most important thing, as I said, was agriculture. In many developing countries of the world, agriculture is a big part of the economy. And in order to achieve higher productivity, most of the times farmers over-fertilize their soils. And as a result, you have nitrate, nitrite, and phosphate, and I'll show you the results for the phosphate in the next slide, being mobilized, especially during monsoonal rainfalls. And if you look at this figure, you will see that the nitrate, nitrite are concentrated. And the first, I think you should go to the previous slide, please. So if you look at the first one, the A figure, the first one, you can see that the nitrate and the nitrate and the nitrite are concentrated much more along the main stem of the river. And the main stem of the river is the place where people withdraw water for various uses. So you can realize that this pollution is a problem, and the focus of the problem becomes more so the main stem of the river, which provides a lifeline for many people. Next slide, please. So what we have done is we have simulated this using the hydrological model SWOT, as well as we have observations here from the Central Water Commission in the blue line. The red line is our simulation, and the black dots are grab samples carried out by one of our collaborators in India. And this is only for a few years, a few months, over a few years. And you can see that these data are all over the place. But thankfully, it's not a difference of an order of magnitude, but it's within the same magnitude, but we have differences. And so taking all the 100 sites, we constructed this wonderful Taylor diagram on the right-hand side, where the standard deviation, root mean square difference, and the correlation coefficient are all mapped. This is all results which are in a paper which has been submitted to the Science of the Total Environment. Next slide, please. Another aspect of fertilizers is phosphate, and phosphate is also something which you have to keep an eye on, because too much of phosphate in drinking water is not good for human health. And once again, when you look at the phosphate loading SMAP in figure A out here, you can see that it's concentrated more along the main stem of the river. Next slide, please. So the temporal variation of phosphate shows a little bit more erratic behavior, especially when you compare it to the observations from the Central Water Commission in blue. But the grab samples with these black stars show a closer relationship to what we simulate. Next slide, please. So I'd like to wrap up my conversation here by trying to come up with some, simple themes. And I think these themes run through the whole ideas in applied science, especially the water resources. And by the way, this project was supported by the Applied Science Water Resources Program by Brad Dorn and John Bolton. So this is what we are trying to do is innovatively combine satellite data along with a hydrological model to help people have a tool to characterize, to make decisions. And in this regard, we actually partnered with numerous people in India to help them use satellite data to better understand the situation, as well as study as a prediction tool for the future. So similar setups can be used to examine land use or climate change for the future. What happens if all the land is changed to forests, or what happens if all the forest land changes to agriculture? And again, the most important part of our work is trying to set up the system so that managers can use this to set policy for irrigation, application of nutrients, and other water use. And this is specifically true in periods of low flows. And again, when we talk about policy, and we are just talking here about water and agriculture, but you can also think about other kinds of water use, like industrial water use, hydropower, and domestic water usage. So I think the applied sciences, especially hydrology, with the data which NASA satellites have observed, precipitation especially, and then more lately the other ones which Christine Lee alluded to, have a great impact on our understanding of hydrology and nutrient fluxes. Thank you very much.
Thank you, Venkat, for that amazing presentation. Up next, Amber McCullum will be presenting about the co-production of tools in Navajo land.
Great. Thank you, Brittany, and thank you all for being with us today. My name is Amber McCullum. I'm an applied scientist working out of NASA's Ames Research Center, and I work on a variety of applied sciences and capacity building projects, such as the RSET program, NASA's Western Water Applications Office, the Indigenous Peoples Initiative, and 2 projects focused on the Navajo Nation that I would like to talk to you about today. Prior to discussing the projects of this talk with some vital lessons learned from my work with our Navajo Nation partners. Relationships are the essential building blocks of any successful partnership. When working with Indigenous groups, we must first establish trust, learn about the community, and have open dialogue of the needs and the potential roadblocks to our work. This sets the stage for co-development, where the cultural context and the pre-existing knowledge systems are central to the project. And finally, capacity building continues throughout the project and beyond to ensure uptake of the tool within decision-making. Next slide. The first project I wanted to highlight is our Navajo Nation Drought Severity Evaluation Tool, or DSET, which if you were online with us for day 1, you heard a little bit about as well. This was created in partnership with the Navajo Nation Department of Water Resources and the Desert Research Institute, or DRI, with funding initially from NASA's Western Water Applications Office and now through the SD Bechtel Jr. Foundation. Next slide. We created a free user-friendly web application to be used by the Navajo Nation for drought reporting. This tool is built as a spin-off of the popular Climate Engine website, which harnesses the power of Google Earth Engine to generate maps and time series of climate data. In particular, of interest to our partners were drought indices, such as the 6-month Standardized Precipitation Index, or SPI. And this is used during extremely dry periods to declare drought emergencies on the nation. These maps, alongside time series of variables such as precipitation, vegetation health, snowpack, temperature, etc., are so vital for monitoring ongoing conditions in conjunction with the monthly ground-based rain can collections that the Navajo Nation collects, as shown here on this image. Next slide. This is what the DSET tool looks like with the Navajo Nation administrative boundaries displayed. This is a region within the four corners of Arizona, New Mexico, and Utah, and it's about the size of West Virginia, so it's a very large area. Here you can see the 110 chapters, which are similar to US counties, that are displayed along with the network of 85 rain gauges with the red markers. And these are the rain gauges that the Navajo Nation collects data from. The panel on the left allows you to select the variable of interest and the statistics such as the total or the difference from average and the time period. Next. You can also generate area averages of the 6-month SPI for each chapter. This is from July 19th, where you can see drought conditions are really severe in the southwestern region. And finally, next. You can also generate time series of these variables, such as the SPI for each of the 5 agencies over the course of the year. You can download the data or figures directly from the tool. And I wanted to mention that just this June, at the end of June, these maps and data were presented to the Navajo Nation Tribal Council, the Navajo Nation President, and their Commission on Emergency Management to reaffirm a drought declaration on the nation. And this allows the nation to disseminate resources and funds for mitigation activities across the nation. Next slide. And finally, we are now working on a project focused on consumptive water use estimates in the largest agricultural region on the Navajo Nation, near Farmington, New Mexico. And we're doing this as a case study through the OpenET tool. OpenET provides monthly field scale estimates of evapotranspiration rates or consumptive water use and is extremely useful for water budget analysis, conservation efforts, and much more. We are now in consultation with our partners for the types of analysis that will be useful for their on-farm production activities, such as things like comparing cumulative evapotranspiration values during drought years. Next slide. So as these efforts continue, we always keep this mantra in mind: water is life. This is something that connects us all. And for us at NASA, it's really the driving force to ensure our data and tools can be used in an equitable and beneficial manner. So thank you all for your time today, and feel free to reach out to me with any questions.
Thank you, Amber. Your presentation was very interesting. Now we'll begin a panel discussion, and John Bolton will be the panel moderator. John, if you'd like to start by introducing the panelists or going over some questions.
Thank you, Brittany. So I think we only have a few minutes for our panelists, Stephanie Granger, Dr. Venkat Lakshmi, and Dr. Amber McCollum. So I was trying to think of what kind of question could be woven through each one of the presentations. And I think a theme that we saw with each of the presentations is the role of technology and connecting with partners, technology for moving the science forward, as Dr. McCollum just mentioned, and also the technology for reaching mutual understanding for needs for partners. So I'd like to direct my first question to Stephanie Granger. And Stephanie, I was curious what you've seen, how you've seen technology and advances in technology and what role it plays for addressing needs assessments and connecting more with our partners.
Sure, John, thanks so much. It's a really great question. I've been at this for a long time, working with Western water managers for well over a decade. And what I've seen is that as in particular, the Western US is facing, greater and greater challenges, there is more openness to using Earth observations and NASA science and expertise to address these challenges. And then where we sort of use technology then to develop partnerships is through the needs assessments is really through communication, understanding what the needs are, what is the technology that is currently in use, and what are those gaps in between the NASA observations and the existing technology that we can fill in order to address some of these needs. Thank you.
Thank you. What I liked about your presentation, one of them, was that how to sustain the partnerships through this technology and sharing of information. Venkat, you're working in the Ganga Basin, and this is a unique basin in for many reasons. I'm curious how you've seen your work being transferred towards informing policy, or the potential for your work to inform policy through this technology and information exchange.
So that's a good question. So we interact and interface with a lot of academics in India, as well as people in the government. One of the things they have tried to do more so in the past few years than more recently is that trying to use data from their own sensors. So the Indian Space Agency launches their own satellites. Unfortunately, some of those data are not very well calibrated. You know, I'm talking about radiometric calibration, so it's not very easy for us to use it. But what they have been doing is they have been doing these kinds of model exercises and planning for the future, and they have been paying a special attention to the deficit of water. Nutrients, not so much, but water, yes. Because, you know, the one thing which has been exposed because of the GRACE work, which Matt Rudell and other people in the GRACE community did, was showing a deep drawdown of water in northwest India. You know, the aquifers are really getting really depleted. So one of the things they have been doing is that, and this is not directly Indian government as much as agencies like the World Bank, which you obviously work with and know them, have been involved in trying to figure out how do you start irrigating smartly at a farm scale. Like, you know, you have the soil moisture, you have forecasted rainfall. How can you use that information to smartly irrigate? And some of these things are just getting off way. And obviously all the data comes from NASA satellites, from SMAP, from GPM, iMerge, etc. So that's where they're going in this.
Thank you very much. Last question, if we have time for it, I'd like to direct that to Dr. McCollum. Amber, I'm very excited about the Navajo Nation work and the DSAT tool. It still just blows my mind that we can do this from satellite, you know what I mean? The question is how do you see the sustainability of this concept and this methodology moving forward and communicating with our partners in the Navajo Nation? And what do you see as the future of tools such as DSAT and NASA Applied Sciences partnership with Navajo Nation?
Thank you, John. Great question. Sustainability is always something that we're continually thinking about, especially with these sort of shorter term NASA projects, right? Where they're a couple of years of funding and then the tool is launched out into the community, and uptake is really important. So a few things that we've tried to focus on is capacity building. So having the end user, the partner, actually using the tool now is so valuable because we can say, hey, it's useful. It's useful for these decisions. And I think the other thing that we've really been doing is trying to get buy-in and support in terms of resources, in terms of funding from our partners through the Navajo Nation, as well as through philanthropic organizations that really care about these things as well. So I mentioned the SD Bechtel Jr. Foundation, helping to support the continuation of our work. And also we've been talking with the Navajo Nation in terms of their recent drought declaration and the resources and funds that come through under a drought declaration. Maybe we may be able to use those funds in support of the continuation of these projects and continuation of these relationships. So that would be a huge success and win for us if we were to get that real buy-in from that partner agency. And I think the final thing I'll mention is sort of leveraging the projects and the resources from other communities as well. So I mentioned we're essentially a spin-off of Climate Engine. And if any of you have heard of that, it's a really popular tool that's being supported through Desert Research Institute, but also through NOAA, NIDIS, those types of organizations. So I think having those collaborators and then finding support and resources through other federal agencies as well as other research agencies and kind of building off of what we're all creating is really valuable as well.
Thank you so much. And fantastic answers from all three of you. And I would like to thank you for your participation and for the audience for your engagement and listening. And now I will pass the baton to Brittany. Thank you so much.
Thank you, everyone. It was wonderful hearing your different perspectives. For our last presentation in this session, Milton Munoz Incapié and Ethan McGee will be telling us about the Develop Hobos Bay Water Resources Project.
Awesome. Thank you so much, Brittany. Hello, and thank you for joining us today. Again, my name is Ethan McGee, and I'll be presenting with Milton Munoz Incapié, and we will be highlighting the Hobos Bay Water Resources Develop project this summer. Milton, take it away. Next slide, please.
Hello, everyone. It's a pleasure to be here, and I will give you a short introduction of our reserve, Hobos Bay National Storm Research Reserve. This one is one of the 29 reserves in the NEARS system, and is the only one in the Caribbean. This reserve was established 40 years ago in 1981, and is located in the southeast coast of Puerto Rico, the smallest island of the Greater Antilles. We have a total of 2,883 acres, and we protect a lot of important and sensitive ecosystems as coral reefs, seagrass beds, mangroves, and dry forest. However, this reserve is the home range of several endangered species as the Antillean manatee, the yellow-shouldered blackbird, and the hawksbill sea turtle. And as a reserve that is located in the Caribbean, we are exposed to several inactive hurricane seasons that threaten natural resources, and also the growing anthropogenic population in the watershed also is a potential source of impacts for the water quality of the estuary, as well as the massive intrusions of or arrivals of the brown algae sargassum, and also several impacts in the mangrove ecosystem and wetland fillings. For us as a research, has been a pleasure to work with this excellent team of interns from the NASA Develop, led by Dr. Juan Torres and Dr. Kenton Ross. And the idea is to have, to have their help to visualize those major changes in the reserve ecosystems, to use this information in the improvement of our management practices. And before let Ethan continue, I would just to say thank you to Adriana, Olivia, Andrew, Liliana Taylor, and you, Ethan. I will let you to continue the presentation. Thank you very much.
Thank you, Milton. So knowing that Hobos Bay is at risk for climate change impacts, our team got to work on our project objectives. Prior to the start of our project, our partners were able to implement and provide years' worth of in situ data, which was instrumental for our project. However, our team was able to use new methodology by combining this in situ data with NASA satellites. This project utilized Landsat and Sentinel, NASA and ESA satellites, and builds upon work that Develop has already done by modifying tools such as RSET's Random Forest Classifier and Develop's Optical Reef and Coastal Area Assessment, or ORCA, tools. Our team had 4 main project objectives that our partners hadn't had the capacity to focus their efforts on thus far. During our 10-week term, we observed coastal change from 1997 to 2020, evaluated water quality parameters such as turbidity, highlighted mangrove forest extent loss over time, and created a high-resolution land use land cover, abbreviated as LULC, analysis that our partners can use in their conservation efforts. Next slide, please. So after we completed our analysis, we were able to highlight several results of importance. The figure to the left shows coastal change in Hobos Bay from 1997 to 2020. We see that this change is shifting towards water, evidence of sea level rise. 17% of the reserve saw a major shift towards water, influenced by major events such as significant rainfall in 2007 and Hurricane Maria in 2017, that both had lasting effects on coastal change within Hobos Bay. Additionally, we saw shifts in turbidity and colored dissolved organic matter water quality parameters, partially due to human impacts such as high boat activity that will change the delicate integrity of the shallow reef ecosystem. Finally, we saw a significant reduction in mangrove forests from 2010 to 2020, seeing a loss of nearly 5 square kilometers or a loss of around 55%, retaining only 4 square kilometers today. Mangrove habitats are very fragile, and even the smallest environmental change can cause disruption of healthy forests, which is evidenced by this coastal change and water parameter shifts mentioned earlier. While we were able to draw conclusions for each of our 4 project objectives, we were also able to connect these results together to create a well-represented holistic view of the bay. For example, we saw a strong connection to turbidity values and mangrove extent loss. Looking at the figure to the bottom right, we see high turbidity values in the eastern inlet of the bay, alongside the mangrove extent change from 2010 to 2020. We see that over a span of 10 years, a huge section of mangrove forest was lost, and turbidity was most likely a contributing factor in this result. Next slide, please. So these are all significant findings that will drastically influence Hobos Bay moving forward. Now we ask the question, why should we care? Well, for starters, Hobos Bay is listed as a national research reserve, so there's a major ecological significance in protecting it and visualizing these impacts. Among the 2,883 acres of protected area, one can find several endangered species such as the hawksbill turtle and West Indian manatee that Milton mentioned earlier. Due to the urbanization in the region and shifts in mangrove forest extents mentioned earlier, watershed dynamics have changed significantly. And this was visualized by NASA satellites by our team. The figure to the left shows the extreme scenario of turbidity changes within Hobos Bay. This visualization highlights the average of the wet season of 2017, where Hurricane Maria was surging through Puerto Rico. While turbidity values are not normally this high, we're witnessing an increase in median turbidity values, exacerbated by more frequent and violent natural disasters. So again, why should we care? In addition to ecological significance, Hobos Bay also acts as an integral part to several local economies, including commercial and recreational fishing, ecotourism, and more. These economies are currently at risk due to climate change impacts, such as heightened turbidity concentrations, which negatively impact the equilibrium of the water composition, which then has adverse effects on the local economy by diminishing fish yield, reducing the aesthetic value of the area, and more. Being able to visualize and highlight these changes is extremely beneficial moving forward. Many people have heard about climate change, but few see it on a daily basis. Because the effects don't happen overnight, it can be hard to engage the community. NASA and ESA satellites can help in this regard by showing elements such as coastal change that aren't accessible to the naked eye. Ultimately, using Earth observations can be extremely beneficial in emphasizing the importance to local communities and how climate change will impact their area specifically. After this developed term ends this week, our partners will have useful visualizations to continue to inform their community. And deliverables such as a story map, which is currently being translated into Spanish, will engage the community by showing different scientific findings in an accessible format. Additionally, this will serve as a baseline for future research to be conducted that will supplement our partners' current research efforts. Next slide, please. So this project was a team effort, and I'm so grateful to work with our amazing advisors and our partners at JBNERR for presenting with me today and working with us throughout the summer. Lastly, I want to thank my 4 other team members, Olivia Spencer, Andrew Althazar, Dr. Liliana Hernandez-Gonzalez, and Taylor Conklin. I could not have done this without all of you. And thank you all for attending, and I hope you have a fantastic rest of your day.
Thank you, Milton and Ethan, and to all of the presenters that have taken the time to speak to us today about their work. With that, I'll officially wrap up the Enhancing Water Management session of today's program. As we transition into the Ensuring Food Security session, please follow the link in the chat to answer today's poll question to help us understand your familiarity with the use of Earth observations. Again, thank you all for your participation, and As you're all filling out the poll, I will now pass things over to my colleague, Haley Pippin, the MC for the next session.
Thank you so much, Brittany. Hello, everybody. My name is Haley Pippin, and I'm the Senior Fellow for the Geoinformatics and the Communication teams with the Develop program, and I'm based out of the NASA Ames Research Center. I will be taking over as your MC for the Ensuring Food Security session. And our first presentation is an overview and history of the NASA Agriculture Program presented by the Agriculture Program Manager, Dr. Brad Dorn.
Hi, everybody. I'm waiting for my picture to come up, but while I'm doing that, I just want to introduce myself as the program manager for the agriculture application area, and I'm also the program manager for the water resources application area. So what does that mean? And I'm hoping my video comes on soon.
You're good.
We can see you, Brad.
Oh, you can? Okay, great.
Yep.
What does that mean? And it's really, really simple. My job is to support and then get out of the way of all the great scientists you heard in the previous presentations and the one you're going to hear now. These are the scientists and the experts that really make this happen. And second of all is to get you excited and hopefully explain why agriculture is such a crucial and key area for applications and the use of Earth observations. Next, please. When you think about agriculture and applications in our area, a lot of our work and a lot of what actually NASA does is we stop at the first bullet. And to be honest with you, there's a lot of work there. We have a lot of factors, a lot of impacts of agriculture, things that we want to get benefits from, and also things we don't want to have those negative impacts on the Earth. And as you can see there, a lot of NASA resources and capabilities that we can apply to, whether it's evapotranspiration, plant stress, yield. Water is a key component to it. But what you might not realize and what is super crucial for our program are the next three bullets, the partnerships. Now, we're tagging the obvious ones there, the big agriculture ministries of the nations, and because food is so crucial, those are often the key areas to go to. But also, what about the producers? What about that whole producer network of industry experts, seed companies, big ag, small ag, local areas, water management. And then the fourth is, how do we enable a community that really gets around the use of Earth observations and using it, the transparency, the objectivity, the criticality of it to help feed our planet and the people on our planet. And so let's talk about this a little bit further. Let's go to the next slide. Just to give you a little perspective, oftentimes I hear, oh, NASA does agriculture. And I want to respond saying, oh, NASA does astronauts. Because actually we've been doing agriculture about as long as we've been doing astronauts. In the early 70s, we had a major global crisis. We had issues with the stocks and the trade and what was being grown where, who was lying to who, and we needed a global system to monitor agriculture. And guess what? 3 months later, after this crisis, there was a little satellite called Landsat-1 that got launched. So you look at those early days of space remote sensing, it is all about agriculture. You even look at the archives in Aeros Data Center of Landsat, you can see what they were monitoring, and it was agriculture, global agriculture. And so let's just step back further. Let's not even go there. Let's step back further and let's go to the 1930s and the Great Depression and in the United States, where we had this major impact on our food supply and our entire economy. What did they do to respond? one of the big things was they enacted a major aerial photography program. No, we didn't have NASA then in the 1930s, but we had airplanes and we had cameras, and we were monitoring Earth observations as a response to that crisis. So the idea is that we are, it's ingrained in Earth observations at NASA, the agriculture application. And so let's go to the next slide, and let's go to, say, 2017. And my boss said, you know what, we need to do agriculture and we need to do some applications differently. We need to do them better. How can we do that? And let's try something. And we tried something what's called NASA Harvest. And that is, we put out there, and the University of Maryland was awarded the ability to go out and really be a program that targets and tries to innovate our ability to get Earth observations into decision makers' hands. And it is so neat to see the speed, the creativity, the innovation. And you're going to hear about that in our next speaker, the director of NASA Harvest, Inbal Becker-Reshef. And so that you're going to hear more about. And then let's go a little bit even sooner in the next slide. So what's going on this year? Well, we got Landsat 9 launch coming up next month. And it was actually out of the Water Resources Program. We actually developed, the team, I had nothing to do with it, developed an ability to really take that thermal band, which we've been doing research on for decades, and turn it into an application. So there you have Denise Moyle, I'm sorry, we have a major crisis out west. And one of the things that's frustrating to agriculture producers all over the world, but especially when there's crises like major droughts and a mega drought, there's no decisions to be made. They're just completely helpless because they rely on water, but they have no control. One way to control it is, can we understand better how to allocate water and what our plants need? And we haven't really had that ability for all farmers, and certainly producers that don't have resources for expensive in situ monitoring. And OpenET has developed a tool that takes advantage of that thermal band, creating evapotranspiration measurements that are then integrated, and that's the key, it's integrated into their decision systems. And that's where we always have had difficulty. And it continues to evolve, and this is going to grow, but it is so neat to see. You're going to see an announcement soon to where we now can get farmers like Denise at least that ability to control that part of their process where they can manage their inputs. And so, such an exciting field, such exciting times. The capabilities are growing, the applications are growing, and I hope you get really excited about our next speakers because they are the best in the world, and they're going to show you some things. And once again, just in this time, it's just the tip of the iceberg. And I hope you get excited about our program and all the applications programs. And I thank everyone. And I also want to call out our Deputy Program Manager, Sarah Brennan, who really helped put together the water resources and the agriculture program set up here. So thanks so much. And I'll turn it over to Inbal.
Thank you for that terrific overview of the program, Dr. Dorn. Up next, we have Dr. Inbal Becker-Reshef to present on NASA Harvest activities and their impacts.
Great, thanks very much, and thank you, Brad, and everybody. And it's a pleasure to be here and to share a little bit more about NASA Harvest, the NASA's Food Security and Agriculture program. And Brad gave a great introduction to this. And what I thought I would do is just start with a little bit of context about, and I think Brad provided a lot of that already, but why should we all be caring about this? And so I think we're all well aware that enhancing food security and resilience are some of the major, if not the major challenge that we face in this century. That's being compounded by the warming weather and a warming climate, with a lot more extreme weather events that are impacting, in a lot of ways, agriculture and our food production. At the same time, population is continuing to grow. Our land and our arable land is not continuing to grow at the same time. And then on top of all of that, we're also now seeing the impacts of the ongoing pandemic. And so I think if a lot of you are probably aware that just today already, 9% of the global population is severely food insecure. And some of the estimates around what the impact of the COVID pandemic is pushing another 100 million or more into food insecurity. And of course, that's primarily impacting the populations are already most vulnerable to food security or food insecurity. At the same time, we still have a huge uncertainty around where food is being produced, how much is it being produced, when. And this kind of information is really important for example, anticipating shortfalls and then being able to be responsive and have early action to respond to these and anticipate those for food markets and prices of grain commodities and for anticipating different countries' trade needs, for example. And so even though we have a lot of uncertainty around this kind of information, there are decisions that continuously have to be made with the information that we do have, and whether that's for trade or whether that's for food security. But at the same time, I think what is really important for us is to be able to innovate around how do we monitor our food? How do we understand better what we're growing, where we might have shortfalls, where we might have surpluses? And we're in a really exciting time around remote sensing. So as Brad said, even though our NASA's involvement in agricultural monitoring goes all the way back, what's different today is that ability to move really out of the research and into operations, both with the developments around our capabilities on the satellite side, in tandem with advances in machine learning, advances in supercomputing and cloud computing, and really being able to advance where we are and the information and the science into operations and into informing decisions. And that's really the focus of our program. Next. And so if you look at just where we are today, a lot of you will have seen and will have noticed that prices of key food commodities and feed commodities like corn have more than doubled in just 1 year. They're now back going down again, but not nearly as low as what they were just a year ago. And this is really important for us to, and I think if you remember what Brad was talking about as some of the food spikes that were back even in the 70s, this is really important. And to be able to avert market volatility, which impacts food security, it is really important for us to have information about where and how much is being produced. And there are a lot of different reasons I won't go into now of why we're seeing that major spike, but one of them is larger imports from China, for example, that were unexpected, the pandemic and a faster recovery that was expected as well. Next slide. Okay, and so that's some of the context for NASA Harvest, which is again NASA's Food Security and Agriculture program launched in 2017, where our main mission is to help advance the awareness and the use, as well as operational uptake of Earth observations in support of food security, in support of stable markets, and in support of sustainable and resilient crop production. And it's also important to note that this is NASA's contribution to the international G20 program called GeoGlam. Next. And so Harvest is a consortium. We have many partners across the agricultural sector. And here are some of the logos of our partners, over 50 partners from universities, from private sector, from public sector, from governments, space agencies, UN organizations, et cetera. And that community is continuing to grow. And that's really how we're able to have the impact that this program has. Next. And so in terms of our portfolio, we're really organized around different thematic areas around productivity, land use, sustainability. And really where our space is being able to bridge, given we're applied sciences program, between the research and into the operation. So we also have a very large focus on capacity development and making sure that everything we do is really stakeholder and end user driven. And so here you see listed the different initiatives that we have under Harvest, the different areas of focus. And I'll just give a few examples. I won't have time to go through all of these, but a few of these, and you'll hear more in detail about some of the components as well later on in this session. Next. Next. And so one of our large areas of focus is, of course, domestic agriculture in the US. We have different areas of focus here. A key one, of course, is around sustainable practices and land management. We have a strong partnership with USDA as well as with USAID. And also, I think one of the key parts of Harvest is also looking at how do we better innovate in our partnerships with the private sector. And so we have a large focus on looking at different mutually beneficial partnerships with the private sector, as we see that as a really key way for innovation in being able to reach the goals of Harvest as well. Next. Another area that's key for us and actually also part of the domestic program in some ways is markets and trade. Of course, we have a very interconnected food system. And so what happens in one large exporting country, for example, or one country has implications globally. And so one of the key areas that we have under this theme is the GeoGlam Crop Monitor. And where we're providing a consensus information internationally around crop conditions in the main production and export countries. And that's what you're seeing here on this map. And the audience for this is really policy makers and economists, so non-remote sensing experts, and really being able to translate that information in real time into information that can then be used for making decisions. Next. And this is, for example, our last assessment. And so what you can see there in reds and yellows are areas of concern for production. And if you recall, again, those kind of increasing prices, especially with extreme weather, any drought or any extreme weather in some of the major production or export countries can have really large implications. And so it is really important for us to continue to track and see how these areas that we're watching here evolve into the future in the next few weeks and months. Next. And so we're not only interested in doing these crop condition assessments, what we just saw, we're also working a lot on quantitative assessments of yield and production, and working on that at different scales, all the way from the global scale down to the field scale with various applications at that, whether that's understanding yield gaps and shortfalls, all the way to more implications on global trade. Next. And next again, and that evolved, and our activity really focused on the big production export countries, evolved into also something called the Crop Monitor for Early Warning. This was really requested and pushed for by the humanitarian community, and in particular USAID FuseNet, on looking at could we bring the international community together and bringing a consensus around crop condition in some of the countries most vulnerable to food insecurity. Next. And so this is looking, that image was looking at hotspots of where we have discrepancies. And this is again looking at just this last assessment that we produced at the end of July on what crop conditions are across Africa, for example. And this has become a really critical piece of information that's used by a lot of agencies and humanitarian organizations in terms of their planning for looking at where there could be shortfalls and planning their mitigation strategies. We've also then had requests growing out of that for developing rapid reports and assessments in areas that are of growing concern. And one of the next ones we will be producing is around the US drought, for example, that's developing right now, and a specific focus on agricultural impacts. Next. And then working and led really by FuseNet and UCSB, the Climate Hazard Center, is looking at not only the implications of the climate forecasts and weather forecasts, for example, in the next 2 weeks to 1 month, but also looking at the longer term forecast, 18 to 24 months, and looking at are there any indications of potential shortfalls, in particular in multiple regions, that could potentially lead to devastating food insecurity conditions. So this is very much a newer project that is growing out of some of the work on the early warning side of things as well. Next. And so this has grown really into both, we are now developing a global crop monitor that brings together these big export-import countries, as well as the early warning countries, as well as we've found that this is a really good mechanism for developing capacity and for national governments and ministries of agriculture to adopt this kind of a system. And you'll hear more about that in particular from, in the African context, from our Africa Harvest lead, Catherine Nakalembe. Next. And again, this is our this is a prototype of the global monitor that's providing now this global context of information on crop conditions on a monthly basis. Next. So again, I won't talk too much about Harvest Africa because there will be a presentation, but we've got a lot of work really focused in Africa and on developing and adapting and building capacity, moving really from that research into operations that's had a lot of impact. And I'll let Catherine talk more about the different kinds of activities and projects that we have under that. More recently, another initiative that we've had is called RAPS, Rapid Action for Policy Support. And what we've seen, especially in the context of COVID, we were getting a lot more requests for rapid assessments that are facilitated by Earth observations in support of various decisions. And one of these was from the Togolese government. They came with a request. They, like many other countries, implemented restrictions due to COVID, and they had an aid program where they were trying to help identify where smallholder farmers were, that they could, it was a program called YOLIM, where they were providing interest-free loans, but they didn't know to locate where all their smallholder farmers were. And they asked if we could develop a map of croplands at the 10-meter resolution within 10 days. And we were able to do that, and that got integrated into this program that I think has now served well over 60,000 smallholder farmers. Next. And so we're seeing a lot more of these requests for rapid assessments. Another one was around the derecho, and again, you'll hear more about this from Mehdi, but we've recognized that this is a really important area for us to be able to grow and be able to be responsive to critical decisions, and where satellite data can help facilitate and inform in real-time decisions. Next, I think I'm over time and I'm nearly done. Next. So as I said, public-private partnerships are a key area for us as a way for innovating, and we're trying to work a lot with US companies and also internationally to help reach a lot of farmers. And I think what we've found is rather than working directly at the farm gate, working with different private sector components and industry has really helped to increase the impact and innovation in terms of the work that we're able to do. And so that's very much a large focus for us. And one of the key areas that we're focused on at the moment next is particularly on sustainable practices, and a new initiative we'll be launching led by Dr. Alyssa Whitcraft is around sustainable and regenerative agriculture, which is a pre-competitive forum for bringing together both the science community and the industry around building the evidence basis for sustainable practices and basically where and when should sustainable practices and what their implications are, whether it's for yield or resilience. And so we're really excited for this initiative. And I'll stop there because I think, again, you'll hear more about our data systems and, of course, being able to serve up this data, integrate different data sets. And you'll see a demo of one of our systems called the GLAM system from John. And so with that, I'll stop and thank you very much.
Thank you so much for sharing that impactful work, Dr. Becker-Reshef. Now, Dr. Mehdi Hosseini will tell us more about using SAR data for damage assessments.
Thank you. Hello, everyone. My name is Mehdi Hosseini. I'm an associate research professor at University of Maryland, NASA Harvest. And here I'm going to briefly explain the study we have done last year in our group to assess the impacts of derecho on corn and soybean fields over Iowa. So derecho happened on August 10th, 2020. It was not just over Iowa, it was on multiple states from Nebraska to Indiana, but the hardest hit was over Iowa. And because the Iowa is the biggest producer of corn and also second largest producer of soybean over the state, it was very important to assess the impacts on the final yield over the state. Based on USDA NAS, Iowa is producing 1/6 of the total corn production and 1/7 of soybean production nationwide. So from the first day after derecho, we started to use remote sensing data to assess the impacts and see how much the impacts was like affected the yield over Iowa. Next slide, please. We tested different source of remote sensing data, both optical and SAR data, and we ended with using SAR data Sentinel-1. And the main reason was that because SAR signal is very sensitive to crop structure and geometry of the crop, and so it was like very good source of remote sensing data for these kind of application. But other than that, the cloud was a big issue to use the optical data. So we ended up using Sentinel-1 data. As you see in this figure, I don't know. Oh, yeah. So you can see two Sentinel-1 images is just intensity at VH. Polarization shows one image 5 days before the ritual and another one 12 days after the ritual, and obviously shows clearly how the ritual impacted the fields. And we can just very simply delineate the impacted fields using intensity, VH intensity, but it's not that simple. I mean, when we are looking at higher, field level, we will see in next slide that it's not like continuous over all the fields. So we needed to look at like a strong model to be able to generate an accurate result for the damage. So one of our methodology was based on using, data before and after the ritual. So it was basically based on a change detection approach. And for that, we needed to have a good amount of ground data to be able to like develop and detect the right threshold for change detection. But our main limitation in this study was we were actually almost lack of ground data. We asked many farmers to send us the pictures of their farm to see which field was impacted and which field was not, but we just received 14 images from 14 fields and all of them were corn, no soybean data, and even just those 14 field data was not sufficient. So we ended up with using it was basically based on just satellite data. And we use a time series of data from 2017 to 2020. And we just compare, from 2018 to 2020, we compare different years of Sentinel-1 data to see, okay, how much of the impact was because of the crop growth, how much was because of the soil moisture, for example, and how much was because of the derecho. So we randomly selected 150 sites over the state for corn and 150 sites for soybean. And then we look at the time series of all these sites for these 3 years for different polarization to first find the right polarization and second find the right threshold for the change detection. Next slide. So yeah, as you see, these are the plots showing the time series for 2019, 2020 for soybean for both VV and VH polarizations. I'm not going to more details on this. We published a paper on that at the Remote Sensing Journal if you are interested in the details, but we ended up using VH polarization because it has more sensitivity to the crop structure, and also we use the threshold of 1.5 dB as a start to detect the crop damage. Next slide. Another thing that we needed was the in-season crop map to be able to detect between corn, soybean, and other land uses. So we generated the in-season crop map using Landsat, Sentinel-1, Sentinel-2 time series of these data. And the approach was based on the deep learning method. So the model was trained using data for 2017 to 2019, and then used time series of data for 2020 to generate this in-season crop map. For validation, we just compare our in-season crop map with 2018 CDL map. If we assume that the total, planted crop and soybean yield over the state would stay similar in different years, we saw that there was like 26% of our classified pixels in the not corn and soybean class. For 2018, it was classified as even corn and soybean. So basically, we use these numbers to justify, to modify our final numbers from damage map. Next slide. So after using the in-season crop map and the change detection approach, we finally generated these maps showing the impacted area for both corn and soybean. The left map shows the impacted area for corn, and then the right is for soybean. The total impacted area for corn was 1.99 million acres, and for soybean, it was 0.6 million acres. Next slide. Yeah, so we also did our estimates at county level, and we generated the impacted area for both corn and soybean. And for each county, the first 5 counties that were impacted the most was Story, Boone, Marshall, Cedar, and Jasper. Again, you see the impacted area for corn in yellow, and the green shows the impacted area for soybean. Next slide. Another activity was to see the level of impact for each field. So basically, we again classified all the impacted fields to 3 different classes: low impact, medium impact, and high impact, and based on using actually different threshold. The low impact and medium impact classes shows like we don't expect those impact on the yield loss, but they probably impacted like the harvest activity. But the most effect for the yield loss was from the high impact class, and it shows in total 1.08 million acres for corn and 0.2 million acres of soybean fields affected by derecho as a high impacted class. Next slide. So for the validation, as I said, we didn't have ground data, unfortunately, for the validation, but what we did for that is we just compare our report, our numbers with what was reported by USDA. We generated these results in August, 2 weeks after derecho. At that time, USDA numbers was like huge. So we just here we look at the USDA report in November, 3 months after derecho, and the final report in January. So the first column shows our estimates. So the total yield loss we expected to be 1.28 million acres, which includes 1.08 million acres for corn and 0.2 million acres for soybean. If we look at the report from USDA in November, they predicted to have 1.08 million acres in total of yield loss, which includes 1 million acres for corn, which is very close to what we predicted, and then 0.08 million acres for soybean. And then the final report from USDA in January 2021 was like a total 0.78. It shows a significant drop, and it was mainly because of the corn, and they predicted, the final report was 0.7 million acres of loss for corn and 0.08 million acres for soybean, unchanged for soybean. So we still see some differences between our estimate and USDA in the final result. And I think it was mainly, we basically, as you said, like the lack of ground data was a main issue for us, and we had some uncertainty on the in-season crop map. So those are impacted, but in general, the result I think was promising, especially if we could now look at the available ground data. We can get that from USDA or any insurance company. We can improve our models. This map actually showing the impacted area, all the fields, and the white color shows the impacted field here. Next slide. If we zoom in like small regions, so we can see even for 2 fields near each other, one could be, fully impacted, and the other one could be non-impacted. So it's important to look at these kind of damage at field scale. Need to look at like medium resolution, high resolutions satellite data. And next one. Yeah, so in this study, actually, we showed that using just SAR data and just time series of SAR data, when we don't have ground data, still we can generate some interesting results for these kind of rapid response activities. But it would be nice to have like more frequent SAR data, so not just waiting for 12 days to get one Sentinel-1 scene. So hopefully by having nice SAR data, I hope we not only have like more time series of SAR data, but I hope, I mean, we get like multi-frequency SAR data, not just looking at C-band, but also looking at combination of C-band, S-band, and L-band, or if we want to also include X-band from TerraSAR-X or other satellites. So again, this like combination, we expect to improve the accuracy significantly as well. So with that, I just finished my talk, and thank you all so much.
Thank you so much, Dr. Hosseini, for that really insightful presentation. Next, I'd like to introduce Dr. Catherine Nokolembe, who will give a presentation on NASA Harvest Africa initiatives.
Thanks, Haley. I hope everybody can see me. If we could go to the next slide, please. I was just kind of to just get everybody to reflect, because we are focusing on the Africa program, so I changed the map a little bit. If we go to our next slide, please, just to give an overview of the main objectives is we want to improve the monitoring systems that are being used. So some of the systems that Mbak shared, like the GeoGlam system. We want to advance the methods that underpin the data that are in the systems. We want to make sure that the results from this are transferred into organizations that can use it across Africa. And we do this by having strong and sustainable long-term partnerships, so we don't do any short-term work. If you can go to the next slide, please. I just like to show this because ultimately, as we combine satellite data, machine learning into creating these great analytics and products such as cropland map, conditions maps, yield maps, we want to ensure that it translates into policy decisions as well as can inform farmers ultimately, and that's kind of the thing that pushes us to keep going. If you go to the next one, please. And you can just skip over this. It's just kind of a summary of the update I'm going to give. This one is just to kind of show, as we're developing the methods and the systems, that they're underpinned by scalable, replicable methods. This work is being led by Dr. Herna Kerna, who's our machine learning lead. It is to ensure that we have sound baseline data on cropland and crop type. We've so far produced really tangible results. This is coming from just 2020, 2021. Mbaz already showed about the Togo cropland map. We've developed one for Kenya, and we're scaling those methods into other countries in East and Southern Africa, as well as in Mali, and trying to do this also at a much higher resolution using planet scope imagery, as you can see on the bottom right, including trying to delineate boundaries for which can help improve some of the crop type and cropland classification, as well as the yield modeling. Go to the next slide. Relating to the yield modeling, Dr. Sajpal Ritvik is leading our yield modeling work. He's developed a framework under using the GeoSIF model, which is really fantastic in the sense that once we have the training data that are required, already pre-prepared using satellite data, we can roll up this methods across multiple countries, but then we still, of course, make sure that the model is calibrated for a specific country and that the results are sound. And he's been able to do this for Kenya, Ethiopia, Mali, Tanzania, Zambia, as well as Malawi. And he's improving this framework, including data from other countries. Most recent result is that considering yield data, including yield data from India, helps improve the model for Kenya. And this is important also for conditions assessments, which feed into the crop monitors that I'm going to talk about in the next slide, please. So improved baseline information on cropland and crop type combined with information on crop conditions, as well as yield, feeds into the national crop monitor systems that have been established in Eastern Africa that are framed with the same workflow and process that is in the crop monitor for AMIS and early warning, as well as the Eastern Africa crop monitor, which is on the top right in that image. In recent months, Lillian Dungu, who is the severe RSMRD East and Southern Africa lead for food security, has been leading training sessions in Ethiopia, Rwanda, and Kenya. This is, tailored towards trying to make sure that the countries are improving not only ensuring that they're taking up newer products and newer methods, as well as more robust data in the process, but as well as being able to leverage any new updates that are coming up in the systems. And of course, countries where we started in Uganda and Tanzania are continuing to publish their reports. If you can go to the next slide, please. And I did mention this, I guess, a little bit, is one of the challenges with developing these robust baseline data sets is the lack of training data, particularly for crop type mapping, as well as for yield modeling at field scale. And we're trying to address this as well through really unique opportunities, such as this funded by the Lacuna Fund, to basically create an unprecedented data set for developing models, which will be made available and open and available to everybody. Street to Sat framework basically is taking data collected by our helmets, people driving on motorbikes or cars with GoPro cameras installed in them. We convert those images using a pipeline we're calling Street to Sat into crop type labels. So basically images that are taken on the road, are straightened, and right now we're using YOLO to create bounding boxes, label the crops, and estimate the distance of where the photo was taken on the road to the actual field. If you can go to the next slide. And in the last couple of weeks, Dr. Kerner and myself were in Uganda collecting data, testing out this framework and pipeline, including working at an ag research station there to collect measurements that then we can translate into making sure that this model and method is scalable before we transfer it to the other 5 countries that will be collecting data at the Lacuna. And just within a week, we're able to collect the data that you can see in the top right on the map. Next slide, please. This is just to summarize, if you want to find out more about Africa work, as well as work under the NASA Harvest in general, please take a look at these. I believe the slides will be shared as well as the recording. There's some interesting summaries, and these are just research articles that have been published in the last couple of months, summarizing some of the methods that I've shown. Thank you.
Wonderful presentation, Dr. Nakalembe. Thank you so much. For our next presentation, we will watch a live demonstration of NASA Harvest's GLAM 2.0 tool by John Kennison.
Hi, everyone. Thank you for having me. My name is John Keniston. I'm a developer at the University of Maryland and with NASA Harvest. And yes, I'll be demonstrating our new GLAM 2.0, which is really an upgrade of an existing legacy system. And what we've done is transition this legacy system that has been in service for over a decade now from more of a time series database to a modern web application. So first, what's GLAM? GLAM is the Global Agriculture Monitoring System, as I've referenced, and it's a web-based platform to enable near real-time monitoring of global croplands. And it does that primarily using the NASA MODIS satellite data, and in particular, NDVI. And yeah, so after a while of use, over a decade of operational use from a lot of different users, we've gotten a lot of feedback from users, taken that into account, and also focused on utilizing new emerging technology. In particular, this new GLAM 2.0 uses what's called serverless architecture and microservices in the cloud in order to create this modern API that we use as sort of the backbone for the new system. So yeah, as you can see, some of these new features that we have in the system are a public API. It's a modern web map with a brand new design, and we are providing a lot of new features, including customizable shareable charts. We've got new interfaces, partnering with different organizations that focus on different regions and different countries around the world. And now we're also, because we're utilizing this new technology, we're able to add different data sets to the system. So data sets beyond NDVI, including precipitation, temperature, and soil water index. So that's just a really brief overview of the GLAM system. And right now I can just go ahead and get to the demo, and just so I have more time. All right. So hopefully you all can see my screen right now. I'll go ahead and give the page a quick refresh. And this is our brand new GLAM 2.0. We have a tour functionality in here that gives new users just a quick overview of the site, but I'll go ahead and skip that for now. But for anyone who's used to using, a web map, this is should be pretty intuitive. We've got our main map area on the center to the right of the page here, and then this panel to the left where we can choose our imagery product. It defaults to this Modus Terra 8-day composite image, and you can find information about all the different products we have just by clicking that little yellow info circle there. So you can see we provide some details about the different products we have in our system. You can see a variety of products from Modus products from both the Terra and Aqua satellites, including the 8-day and 16-day composites and near real-time NDVI product. And as I referenced before, now that with this new system, we have the ability to add multiple different products here. We've got precipitation, temperature from ERA2, and NDWI and soil water index. And we plan on adding additional products to the system in the future as well. So using this dropdown, we can select our product very easily. And as you can see, as soon as you select your product, it appears on the screen. And then we can select the date of our product using this little calendar dropdown, where we can toggle back and forward in time, or we can use just these buttons to jump back and forward in time as well. In addition to just visualizing these data sets for each date, we can also visualize the anomaly for these data sets. So for example, if I move this toggle over to the 5-year anomaly, we're now looking at the anomaly from the 5-year mean for this data set on June 26th for this 16-day composite. So you can see this legend at the bottom left here shows you that anomaly color map, and you can see some of these areas where we're deviating from the mean for the last 5 years, whether negative or positive. And this legend also shows you the full compositing period for this data set. In this case, we're looking at a 16-day composite for this Modus NDVI data. So not only can we view the anomaly visualization, we can also apply a crop mask to our visualization. In the new system, we have a variety of new crop masks, including crop masks provided from partners in different countries. For example, Canab in Brazil has provided us with many different crop masks specific to different regions or crops in Brazil. We also have, you can see we've got crop masks for Argentina, Mali, Chile. But for now, I'll just go ahead and turn on one of our global crop masks provided by the GeoGlam Crop Monitor project. So I'll just, if I select soybean here, and it's loading a little slow right now, but there you can see now, instead of viewing the entire composite, we are now only looking at data for within our soybean crop masks. And if I turn off the anomaly there, we will probably be able to see it a little better. And of course, with any demo, something has to be a little slow now, but maybe if I get a different date loaded, it'll work a little faster. Okay, I'm going to give it a quick refresh and let that imagery load up. But one of the great things about this new system too is the new analysis tools that we have. So in the example I'm going to give today is just a basic time series for a certain administrative region. We also have the ability for a user to draw their own geometry and generate statistics, or the user can upload their own geometry. Right now we have support for GeoJSON and KML, and we're adding the capability for a user to upload their shape files at a later date. But for right now, I'll do an example just using one of these administrative boundaries that we already have in the system. And at the bottom right here, when you look at the layers available, we have what we call the admin 0, which is our these national boundaries, or admin 1, and you can see these are our sub-national boundaries. So we can generate a time series for any of the regions in these layers. I'll start with these admin 0 for now. So I can either, once I toggle on this regional analysis tool, I can select a country either by just clicking on it, or I can choose one from this drop-down list here. But I'll start off with a really basic example. In Brazil, and we were looking at our soybean mask before, so I'll turn that back on. And you can see these are the NDVI for our soybean cropping areas in Brazil. And then you can see in this form, we have a lot of different options. So we've already selected our country. We have the 8-day NDVI composite selected. And now I'm going to go ahead and select soybean for our crop masks. And then just to create a really simple time series, I'll just click the last few years to get a look at the situation here. And you can see one of the nice things with this new system is that we can drag and rearrange these windows a little bit. So if you're really interested in looking at this chart more than the map, we can resize this, and then we can resize this chart right here. So now we've got a nice looking time series for the NDVI for Brazil, just for our soybean cropping areas over the last 3 years. And now that we've got this chart generated, we can download it as a PNG, JPEG, SVG. We can print the chart. We can view it in full screen. We can also view the data behind this chart. Once it generates the chart, it also generates the tables of the data behind it. So you can see, we can toggle through the different series here. And one really nice thing that we've added to the new system is the ability to share these charts on social media or just by generating a link. So you can see this share symbol right here provides the ability to copy a link, or you can share it directly on social media. You know, it generates this Twitter link for you right here. So I can go ahead and tweet that out. And then another nice thing that we've added to this system, and I'll create a more complex example, is for instance, you wanted to compare 2 different regions on this map here. So I'll go to our admin 1 layer, our subnational region layer, and I'll select a few areas that I want to compare. So let's say I want to do a more complicated example, and I want to look at the mean for this region in Brazil. You know, let's say I want the mean for the last 5 years compared to this year. I'll go ahead and generate that. And then let's say I want to compare that to another region in Brazil. Let's choose Sao Paulo. And I'll keep all these same properties selected in the form, just changing this region here. And I'll go ahead and add that to my list of charts here. So we've got our charts generated. with the limited space on the screen here, it might be a little bit difficult to look at. You can rearrange them to get a better picture. But one of the nice things that we've added is this new stats only dashboard. So you can see I clicked on that link and now I've set myself to a dashboard where there's no map taking up any large part of the screen. So now I can really get a look at these charts and do some analysis here. So this is a really simple example and just a piece of what this new GLAM system can do. And again, all of this is, the magic behind this is this new API that we're using, that we've created with Amazon Web Services and a serverless architecture. So all these stats, all these map tiles are being generated on the fly as they're requested. And if you'd like to learn more about this system, I encourage you to go to the site at glam.nasaharvest.org. And if you open this little help panel here, you can see more information about GLAM, and you can find some other facts and resources about this system. And I encourage you, if you're interested, to sign up for our newsletter and also sign up for our user group about the system. And if you're a developer, there's also information here for you to access the API. So with that, thank you for watching this demonstration.
That is such a powerful tool. Thank you so much for that demonstration, John. Finally, we're going to close out our session with a presentation on the Develop Midwest Agriculture Project presented by Joel McClure.
Hey, thanks, Haley. Everyone hear me okay, right?
Sound good.
Okay, perfect. Hi, my name is Joel McClure, and I'm representing NASA Develop's Midwest Food Security and Agriculture team, comprised of myself, our team lead, Sophie Berriman, Abida Ansari Ansa, Cameron Levine, and Julian Liu. Our project is leveraging NASA Earth observations to analyze and display crop phenology data and weather conditions to support expansion of small grain crops in the Midwest. Next slide, please. Okay. Cool. Our project was driven by three primary concerns. First, corn and soybean monocultures pose serious environmental consequences, such as soil degradation, fertilizer runoff, and biodiversity reduction. Second, socioeconomic pressures to maximize yields and maintain traditional management values make it difficult for farmers to diversify crops and cultivate small grains. And third, while including small grains in crop rotations have numerous ecological and economic benefits, limited data about their growth and yield means a lack of insurance coverage options for farmers, which makes switching to small grains even more financially risky. In the Midwest, an area dominated by corn and soybean monocultures, the Practical Farmers of Iowa is a leader for crop diversification and promoting the growth of small grains for sustainable agriculture. The Practical Farmers of Iowa provide cost share programs and provide resources to help farmers move away from corn and soybeans. On the left on this slide is our study area map showing the locations of 100 small grain crop fields ranging from 2 to 228 acres across Iowa, Minnesota, and Wisconsin. These farmers uniquely integrated small grains such as oats, wheat, and rye into their crop rotation between January 2017 and December 2020. In addition to PFI, we also collaborated with the USDA Agricultural Research Service and USA National Phenology Network. There's a desire among farmers to expand their cropping practices, but there currently isn't an easy way to access and visualize the available data for their specific farms. We hope the tool we created during our term will provide an easy way to access this information. Next slide, please. Okay. Our project started this spring with the Term 1 team who developed the initial code for our phenology app. This is an online, free, publicly accessible Google Earth Engine tool where small grain farmers or PFI farmers can compare their crop performances to other farms in the program. Our 2021 term refined the Google Earth Engine framework and built a graphical user interface so the Practical Farmers of Iowa farmers can visualize and compare vegetation indices and phenologies of their small grain crops to other farmers' fields and historical records. Additionally, we created the regression model to validate the relationship between small grain crop yield and different vegetation indices such as NDVI. Keep click, please. Okay, cool. This flowchart highlights the methodology we used to create the data that would be displayed in the GUI and used in the model. The previous term combined the images from NASA satellites Landsat 7 and 8. From this merged imagery, we calculated vegetation indices such as normalized difference vegetation index, NDVI, soil adjusted vegetation index, enhanced vegetation index, normalized difference water index, and the simple ratio of near infrared and red bands. which all measure different aspects of crop health. We used a variety of indices in order to capture as much information about these fields as possible using the information available. So these indices were then combined with climate data for GridMet, precipitation and temperature, and yield data and farm boundaries from the Practical Farmers of Iowa. And then it was incorporated into the Phenology app and used in the regression model to support our results. Next slide, please. Okay, this slide shows the user interface for our Google Earth Engine app. The top left is what the farmer will see after they run the app for their farm, after putting in their unique field ID, which is for them, their planting and harvest dates. The left side of the app shows the graphs that are shown on the rest of the slide. And then the GIF shows our field of interest in true color on the left and NDVI on the right. This is useful to show in-field variation and also give the user a way to associate NDVI with something they can easily see on the ground, which is the true color imagery. The chart below shows the min and max temperature for each day throughout the year, as well as the precipitation. Farmer will be able to use this chart to look at the temperature and precipitation variation throughout the year. The upper right chart shows the NDVI values of a rye crop for Floyd County, Iowa. In 2018, the solid green line is the mean NDVI, while the light green shading shows the data range for that point, the min and max. The NDVI before planting date in May shows the reflectance of cover crop mix, and the values from May through September show the growth of the crop throughout its growing season. Like most grains, the NDVI will peak about a month before the harvest, where they start to turn brown and are ready for harvest. The lower right chart shows the same NDVI curve as above, just overlaid with the values for the rest of the farms growing that same crop in that state, in this case, Iowa. This chart can be used by farmers to compare the growth of their crops and see how it compares to other fields under similar growing conditions. Next slide, please. For a regression model, we wanted to understand the relationship between the vegetation indices and the small grain crop yields. We focused our analysis on oats because it was the crop with the most available data. And then we used a generalized additive model to explore the relationships. In this model, a higher R² and higher model fit percentage is indicative of a more predictive model. As you can see on the table on the left, the mean NDVI on its own yielded a very small R² and a poor fit. Through adding other mean vegetation indices, we were able to increase the R² and fit. However, the best results came from a combination of NDVI associated metrics during the early season months. The chart on the right visualizes the most explanatory model and the nonlinear relationship between the mean April NDVI and yield. While the vegetation indices alone can't predict yield, this combination shows that easily accessible mean NDVI values in the early growing season are indicative of yield. Using this information will allow the farmers ample time to implement adaptive management strategies for their field throughout the entire growing season. Next slide, please. The Phenology app and regression model will help PFI promote small grains throughout the Midwest by enabling farmers to monitor their crops' progress and compare it with historical data. This will support their management decisions and better equip them to grow small grain crops. For example, PFI can keep track of the successful small grain farmers and communicate with other farmers in the area under similar growing conditions. Farmers using this information could feel more confident in their decision to switch to small grains, knowing previous farmers were successful and that they have a tool to monitor progress. Our regression model supports the interpretation of vegetation indices in the Phenology app, with our results pointing to a relationship between early season NDVI and yield. Farmers can keep this in mind as they use the app to inform their crop production decisions. These tools will hopefully help PFI expand their program by showing Midwest farmers the viability of small grain crops and help them make informed decisions about diversified crop rotations and associate or advocate for more expansive insurance policies to protect small grain crops. Next slide, please. Thank you to our previous contributors, partners, advisors, and the center lead for their support. We thank you for attending our presentation at Earth Sciences Application Week. Thank you so much.
That is a huge amount of work that you all accomplished in a short time. Thank you so much for sharing it, Joel. Now, finally, I want to thank you all so much for attending today's plenary session and give a huge thank you to all of our presenters. Please join us at 2:15 p.m. Eastern Time today for the afternoon symposium on Microsoft Teams. Information on the events happening today and the different speakers can be found on the agenda on the Earth Science Applications Week events webpage, the same page that you went to register for this event. And the links to join these afternoon sessions are listed there as well. We hope to see you there soon. Have a great day.